Every server has a limit, a finite amount of CPU, memory, and connections. Push enough traffic at any server and it will slow down, then fall over, then crash. And when it crashes, it doesn't just reject the extra traffic. It drops everything, every legitimate user, every active connection, often taking connected services down with it, in a cascading failure. So here's the problem every real system has to solve. How do you protect a server from too much traffic, an attack, a buggy client, or just viral success, without taking down the users who are behaving normally? The answer is rate limiting. It's the bouncer at the door of every serious API on the internet. And it's one of the most common system design interview questions. There is the kind that quietly separates junior candidates from senior ones. Let's go deep on how it works. Rate limiting protects systems from being overwhelmed, and the threats are more varied than most people think. 1. Malicious attacks. A DDoS floods your API with millions of requests to exhaust your resources. Rate limiting caps how much any single source can send. 2. Buggy clients, more common than attacks. An app with an infinite retry loop hammers your API thousands of times a second by accident. Rate limiting protects you from your own users' mistakes. 3. Scrapers and abuse. Bots scraping your content, credential stuffing your login, people abusing a free tier. Rate limiting makes these economically unviable. 4. Fair allocation. Even with zero bad actors, if one power user eats 90% of your capacity, everyone else suffers. And 5. Cost. Every request costs money, so a rate limit is also a spending cap. So rate limiting isn't just a security feature. It's stability, fairness, and cost all at once. Before the algorithms, let's see what every rate limiter actually does. It's 4 steps, and they're the same regardless of algorithm. Step 1. Identify the client, the key. The limiter extracts a key from the request. The user ID, the IP address, the API key, or a combination like user plus endpoint. Step 2. Check against the limit. Look up the current state for that key and ask, does this request fit? Is the counter below the limit? Does the bucket have a token? Step 3. Decide and update. If it fits, allow it and record it, increment the counter, or take a token. If it doesn't, reject it before doing any expensive work. Step 4. Attach headers, the limit, how much is left and when it resets, so the client can back off. And when the limit is exceeded, the client gets HTTP 429, too many requests. That 429 is the universal, slow-down signal of the internet. The simplest algorithm, the fixed window counter. Divide time into fixed windows, say 1 minute. Count the requests in the current window. When the count hits the limit, reject everything until the window resets. Why it's appealing? It's dead simple. 1 counter per key, minimal memory, easy to implement. But here's the fatal flaw, the boundary burst. Say your limit is 100 per minute. A user sends 100 requests at 10:00:59, the very end of window 1. Then 100 more at 10:01:00, the very start of window 2. Both are within their own windows. Both are allowed. But that's 200 requests in a 2-second span, double your intended limit, concentrated in an instant. For a limiter whose whole job is preventing bursts, that's a serious weakness, which is exactly why the sliding window algorithms exist. The sliding window log fixes the boundary problem by tracking the exact timestamp of every request. When a request arrives, drop every timestamp older than the window, say older than 60 seconds. Count what's left. Under the limit, allow it and log its timestamp. At the limit, reject. Because the window is always measured relative to now, the last 60 seconds, always, there's no boundary to exploit. The burst problem disappears completely. The cost? You store a timestamp for every single request. A user making 1,000 requests means 1,000 stored timestamps. Across millions of users, that memory adds up fast. So the sliding window counter is the pragmatic middle ground, what a lot of production systems actually use. It keeps just two counters, the current window and the previous one, and estimates the rate with a weighted average based on how far you are into the current window. It's not perfectly accurate. It assumes the previous window's requests were evenly spread, but the error is small. The memory is tiny, just two numbers per key, and it smooths out the boundary burst. For most APIs, this is the sweet spot. Token bucket is probably the most popular rate-limiting algorithm, and the one interviewers love most because it elegantly handles something the others don't: controlled bursts. The model, a bucket, holds tokens. Tokens refill at a steady rate, say 1 per second. Each request removes one token. If the bucket is empty, the request is denied. And the bucket has a maximum capacity, so tokens can't pile up forever. Two parameters define it: bucket capacity, the maximum tokens, which is your burst allowance, and refill rate, how fast tokens are added, which is your steady-state rate. Here's the magic. When traffic is quiet and the user makes no requests, tokens accumulate up to the capacity. Think of them as saved-up permission to make requests. Then when the user suddenly fires 10 requests at once, they can because they saved up tokens. That models real behavior. Usage is bursty. Someone opens an app, fires several requests, then goes quiet. Token bucket accommodates that while still capping the long-run average. Why it wins in practice? It's easy to understand, it handles bursts gracefully, and it's memory efficient. You only store a token count and a last refill timestamp per key. It's why AWS, Stripe, and countless APIs use it. Its one weakness: very short bursts bigger than the bucket itself. The Leaky Bucket is Token Bucket's cousin, but with the opposite philosophy. Instead of allowing bursts, it smooths them out. Picture a bucket with a leak at the bottom. Requests arrive at irregular intervals and wait in the bucket, then leak out at a steady, constant rate. If the bucket overflows, too many requests queued, the excess is dropped. Use it when the system downstream needs a predictable, even flow. A payment processor that can only handle a fixed number of transactions per second, or a video stream that needs steady pacing. The trade-off: it doesn't allow bursts at all, even when you have spare capacity, and queued requests wait, adding latency. Token bucket favors responsiveness. Leaky bucket favors smoothness. That's the core distinction. Everything so far assumed one server. Real systems have dozens, behind a load balancer. And this is where interviews actually test you. The problem: if each server keeps its own counter in memory, the limit is multiplied by the number of servers. 10 servers, each allowing 100 per minute, means a user can actually make 1,000, 100 to each. Your rate limit is silently broken. The solution: centralized shared state. All servers share one source of truth for the counters, typically Redis. Every server checks and updates the counter in Redis, so there's one global count, no matter how many servers you run. But that introduces a new problem: race conditions. Two requests hit two servers at the exact same moment. Both read the counter, it says 99. Both think 99 is under 100, allow it. Both increment to 100. That's two requests allowed when only one should have been. The fix: server-side Lua-scripting bundles the read, the count, and the write into a single atomic operation. Redis runs it atomically. No other operation can slip in between. Check-end increment becomes one indivisible step. And one more trade-off worth knowing: production rate limiters often choose availability and partition tolerance over strong consistency, an AP choice from the CAP theorem. If Redis is slow or briefly unreachable, most systems would rather allow a few extra requests than block legitimate traffic. Being slightly permissive beats taking your API down. So which one do you use? There's no single best algorithm. Each encodes a different model of time, fairness, and burst tolerance. The logic need to allow bursts, token bucket, need to smooth traffic to a constant rate, leaky bucket, need accuracy at a reasonable cost, sliding window counter, simple internal service, fixed window is fine. In an interview, the strongest answer isn't naming one algorithm. It's walking through the trade-offs and picking based on the specific requirements you're given. So to bring it together, rate limiting protects systems from overload. Every limiter identifies a key, checks a limit, decides, and returns headers, with a 429 when the limit is hit. 5 algorithms, each a different trade-off. And in distributed systems, shared Redis state, atomic Lua-scripts, and availability over perfect consistency. It's one of the highest value system design interview topics because it touches algorithms, distributed systems, race conditions, and real trade-offs all at once. Subscribe for more system design fundamentals. Load balancing and caching are coming next. And drop a comment. Which algorithm does your API use?